All right, good morning, everyone. So make sure you finish your third test by tonight at midnight. So if you happen to forget that that's a thing, well, just make sure you get it done so you don't lose out on points from a test. We are 3/4 of the way through the semester. So we are like almost done. I mean, we've literally got 3 weeks of lecture and then it's finals week. So just last little push, make it happen, and then you can be done with chemistry until your next chem class. So a couple things, I'm trying to think about what, if you have any late labs, late homework assignments that you've been wanting to try and squeeze in, email me and I can see if I can make something work to give you partial credit at least. We just want to start to like try and get, as many points as we can, maximize as many points, especially if you think your grade's sort of on the cusp. If you're like at a B, C, trying to get as many points so you can push yourself over into that higher grade range. So I think that the last 3 chapters, in my opinion, are a little bit easier than the prior 3 chapters. I think they're just a little bit more straightforward than all the stoichiometry stuff and balancing equations. So next chapter is specifically talking all about gas laws. Share my screen with y'all. Gases are a very unique state of matter. So they have their own relationships because they're so, they have so much kinetic energy and there's such a high temperature and high space between them that particles don't really interact with each other. And that allows you to have these rules that are really nifty and consistent, but they only work for gases. The things that we're talking about today don't work for liquids and they don't work for solids. There's too much interaction between adjacent particles. So this is asking you extra long straws. Have you ever done that when you were a kid? You took like a bunch of those straws and you thread them together to see how long your straw could be. I used to do that at the movie theaters. Well, how long could the straw be? Could the straw be infinitely long if you had a very strong suck? No, there is actually a maximum length for how long that straw can be. We'll talk about why, if you had a perfect straw, so the straw material didn't bend, you were, the straw, let's say the straw was attached to like a really strong pump. So it had like a perfect suction. How long could the straw be given the current atmosphere? Well, couldn't really be longer than 10.3 meters or about 34 feet. After that, it wouldn't work. Why is that the case? Well, we have to talk about this idea of pressure. So pressure is the force that is being exerted per given area. So it's force over area. And when we're talking about a gas specifically, it's the force that the gas molecules are exerting over the surface. And the surface could be a solid, it could be a liquid, whatever it happens to be. At Earth's sea level, the gas molecules in our atmosphere will exert roughly 100,000 newtons per meter squared. If you've ever taken a physics class, a newton is a unit of measurement for force. Meter squared is an area, right? You might be more comfortable with 14.7 PSI or pounds per square inch. Okay. What is happening, or we can also say that it's 1 ATM or 1 atmosphere right at sea level. So if we're at sea level, why does a straw work? Well, there is a pressure inside the straw and there's a pressure outside the straw, right? The atmosphere is pushing down on this liquid. When you aren't sucking on the straw, the pressure inside the straw and the pressure outside the straw are equal to each other, right? Because the straw is open to the atmosphere. So they're both experiencing a consistent atmosphere or a consistent pressure. When you begin to suck on this straw, you create a lower pressure environment in the straw, right? You're removing air from the straw, you're taking it out. So there's a lower pressure inside the straw, but there's the same amount of pressure outside the straw. And so that will force the liquid up into the lower pressure environment. This atmosphere, or the atmospheric pressure, is literally pushing down on the fluid, and that fluid is going to fill into the space where there's lower pressure. Well, there's only so much pressure happening from the surrounding atmosphere. So if we were to attach this to a pump, and it's a perfect suction pump, the pressure exerted from the atmosphere, which is 14.7 pounds per square inch, only has enough force to move the straw up to roughly 10.3 meters. If we were on a planet that had a higher atmospheric pressure, we could see that line go up higher. So why do straws work? They work because we're creating a pressure difference, right? You're sucking the air out of the straw, which is creating a lower pressure environment. The pressure around it is staying the same, so it's pushing on whatever the liquid is, in this case, orange soda, to allow it to rise. So that is an example of how gases work, how we can shift pressure by the amount of gas, a couple other things. So let's look at, for gases, the kinetic molecular theory. This is a model to help us explain the behavior of gases. It predicts the correct behavior for most gases under most conditions. Like other models, though, the kinetic molecular theory is, somewhat of an oversimplification of what's actually happening in reality. So it does start to break down under certain conditions. For this class, we're going to stay in the area where it works perfectly. So you can assume for this class that the kinetic molecular theory is good. So here are a couple of the ideas that go along with the kinetic molecular theory. One, a gas is considered a collection of particles that are in constant motion, and specifically constant straight line motion. So these particles aren't going to be like, they're going to go straight forward and back. There are no attraction or repulsion between adjacent particles. That's a really important thing. So, when we're in a liquid or we're in a solid, the particles that are next to each other, the molecules or atoms, they kind of stick to each other, right? That's what gives it that liquid quality or the solid quality. That's not happening in a gas. These things, we can kind of think of them as being totally isolated from each other. If they do happen to bump into each other, they're acting sort of like billiard balls where they hit each other and then they just move in the other direction. There's no clumping together and there's no like repulsion. A lot of space between particles compared to the size of the particles themselves. So gases are mostly empty space with a small amount of matter. And then the last thing here, the speed of the particles increases with increasing temperature. So the hotter your gas is, the faster those particles are going to move. Here's another way of saying some of these. A gas is a collection of particles that are in constant straight line motion. Okay, so they have a straight path. The gas particles don't interact with each other, don't attract or repel. There's a lot of space, and the average kinetic energy, which is the energy of motion of the particles of the gas, is proportional to the temperature, specifically the temperature in kelvins. As you increase your temperature, they're going to move, the particles are going to move faster and you're going to have more energy. You're going to burn yourself much worse with a hotter gas than a cooler gas. So because of the kinetic molecular theory, hopefully some of these properties of gases start to make a little bit more sense. Like, remember when we said gases are compressible, okay? Are solids and liquids compressible? No, but gases are compressible. Well, let's think about what the kinetic molecular theory tells us. It tells us that it's mostly empty space. So there's a lot of room to move those particles closer together, all right? Gases assume the shape and volume of the container that they're in. So if I have like a little container of compressed gas and I open it, it's going to fill the entire space of the room. Well, why would it fill and stretch out the entire space of the room? Remember, gases, the particles don't interact with each other. So the gas isn't going to like clump together in the shape of the container. It is going to spread out because they're moving in random straight motion, and they're not like gravitating towards each other. Gases have lower densities in comparisons to liquids and solids. Yeah, I mean, because they're mostly empty space. So here's our compressibility. Look at all the space that we have here. The piston can push down to create a gas that's just got a higher pressure. Liquids are not going to be compressible, and neither are solids. Gases, so here's that image of the container of gas. These things are totally isolated from each other. They're not attracted to each other. They don't feel any need to commit or stay together in this clump. So if I open this, they're just going to continue that straight line motion out until they've sort of equalized with the room that they've filled or space. And gases are very low density. So if I had 1 can of pop and I decided to convert it into a gas, 1 can of pop would actually be roughly 1,700 cans of gaseous pop. Okay, so lots of space. So when you say that a gas is exerting pressure on you, it's because the gas particles are in this constant motion, right? So they're constantly hitting the surfaces around you. So as you sit at your desk, there is a certain pressure that's being exerted on every surface of your body from the atmosphere around you. The gases are hitting ping pong in your face, right? Our skin isn't sensitive enough to feel that, which is good because it'd probably drive us insane. But that is occurring. Now, we can increase pressure, right, by adding more air, or we can decrease it by releasing or taking air away. So think about what happens when you go up in an airplane. The pressure is decreasing. The only way you really probably notice that decrease in pressure is in your ears, because they do try and pressurize the cabins to make it comfortable. This idea of pressure is why, or differences in pressure is why we can drink out of straws. It's how we inflate basketballs. It's how we breathe, or when we inhale, we're inflating our lungs, we're increasing the pressure in our lungs. When we exhale, we decrease that pressure. Pressure differentials also are responsible for all of the weather and wind and atmospheric stuff. So when you're going up in an airplane, we mentioned this, that's a kind of a opportunity for you to feel pressure differentials. When you're at sea level or on the ground, the pressure inside your body and the pressure outside your body are the same. So your eardrums are feeling an equal amount of pressure or equal amount of collision from the inside of the body and the outside of the body. When you go up in an airplane, the pressure inside your body is higher than the pressure outside your body. So the collisions are more because you have more air inside your body than you do outside the body. So what do you have to do to get rid of that obnoxious feeling in your ears is you need to, like, quote unquote, equalize the pressure or release the pressure from your body. So how do you do that? Yawning, popping your ears, chewing gum, anything where you can decrease the pressure inside your body so that your eardrums aren't being stressed. The same thing happens when you're going down, right? But when you're going down in an airplane, the pressure is greater on the outside and lower inside your body. So again, you need to equalize. This idea of pressure, if you've taken a physics class again, it's force over area. So the more collisions, the more force you have over a given area, the higher pressure is going to be. This mason jar up top is a lower pressure than the mason jar on the bottom, which is a higher pressure, solely because this has more particles to create more collision. The fewer the gas particles, the less collisions you're going to get. Some of the units of pressure, the one that we use quite a bit and the simplest is the ATM, or the atmosphere. The atmosphere relates to sea level, okay? So we've given sea level an atmosphere of 1. As you move up, like the side of a mountain or away from sea level, your atmosphere will decrease. So we're sitting something a little bit less than 1 ATM, not a dramatic amount, but a little bit less. The SI unit, so the standard unit, is the Pascal or the PA. And this is defined as 1 Pascal is equal to 1 Newton per meter squared. Remember, what is pressure? Pressure is force You dying on me? Okay, and it's not working for me here. I'll just hop back in the slide. So remember, pressure is force over area. So Newton is just a unit for force. Area is any distance squared, right? It could be meter squared, could be foot squared, all sorts of different things. How does the Pascal relate to the atmosphere? Pascal, this 1 Newton per meter squared, is equivalent to roughly 100,000, or 100,000 of those is roughly equal to 1 ATM. So you are experiencing at sea level quite a few of these Pascals. All right, all these conversion factors, or all of these are conversion factors, so you can use these to convert between units. There's another unit that you've probably seen if you are into weather systems, which is mmHGs, or millimeters per mercury. What does the millimeter per mercury mean? Well, remember when we were talking about that straw situation, like how far could the soda pop rise? Well, what if instead of using liquid soda, we used mercury? Well, if we're in a perfect vacuum and we're at 1 atmosphere, so we're at sea level, the amount the mercury will rise given that pressure at sea level is 760 millimeters or 76 centimeters, okay? So at sea level or at 1 ATM, you are equivalent to 760 mm's of Hg. So 1 ATM is equal to 760 millimeters of mercury. There's also another unit called a torr. A torr is the same thing as a millimeter of mercury. Okay, those two things are equivalent to each other. So real easy to convert between mmHg and torr, you just change the unit. You may have heard of a PSI as well, right? If you fill up your bike tire or your car tires, we use PSIs, or pounds per square inch. 1 ATM, or sorry, over here, 1 ATM is equal to 14.7 PSIs. So the equivalent of 1 atmosphere, 14.7. So usually, not usually, all the time, things that we inflate will be something higher than this, right? Our basketballs, our tires, they need to be higher than the atmosphere that we're dealing with at sea level. Otherwise, they won't inflate. So here's all the different units. This isn't anything too tricky. It's just basic conversions. So I want you to, well, here's an example. I'll give you another one, but let's say it says convert 0.311 ATMs into millimeters of mercury. Well, we know that for every 760 millimeters of mercury, we get 1 ATM. So we just do a quick conversion, right? 1 ATM on the bottom to cancel, 760 millimeters of mercury, we get 236 millimeters of mercury. Nothing revolutionary here from what you have done all semester. Let me give you one problem. Just a quick conversion. How many ATMs are in 845 millimeters of mercury? How many ATMs are in 845 millimeters of mercury? I'll give you a minute for that. right, so just an easy conversion, because a lot of the equations that we're going to be learning later, you got to make sure you're in the right units. So if the information is given in millimeters of mercury, but you need to have it in ATMs, you want to be able to convert pretty fast. So we've got 845 millimeters of mercury. We want ATMs. We want to get rid of mmHgs. So 1 ATM is equal to 760 mmHgs, or we take our 845 and divide it by 760 and we get 1.11 ATMs. So our pressure is just slightly above sea level, right? Because 1 ATM would be our sea level. Okay. So why are they pressurized? One thing is it's just more comfortable for your ears, so you don't have that huge pressure differential. But the more important reason that they pressurize cabins is because you are flying so high that the atmospheric pressure is actually below 0.5 ATM. So it's less than half of what you're used to receiving on at sea level. Well, if you're receiving half of the pressure, you're also receiving half of the oxygen. So you would have a huge decrease in oxygen levels, which can include dizziness, headache, shortness of breath, so and so. So if there is, if you have ever been on an airplane where it depressurized or seen it in movies, what happens is those oxygen masks drop down to provide you with enough oxygen so that you don't pass out. That would be terrifying. I've never had that happen to me before. I don't know, has anyone in here had that happen? No, I don't see any yeses yet. I think I would never get on an airplane again. I already have to have like 3 cocktails to get on an airplane, as is. All right. So we're going to move into a series of laws or rules. And all of these, again, just apply to gases. So the first one is Boyle's law. And again, I'm not like a stickler. I'm not gonna be like, which one of these is Boyle's law? But you do need to know how they relate to each other. So Boyle's law is going to relate pressure and volume. Even before we talk about that, the different variables that we're gonna see over the next chapter are changes in pressure, volume, temperature, amount. I'm going to use a lowercase n, amount as in like moles, right? The amount of gas. So those are going to be our variables. So pressure, volume, temperature, and amount of gas. As we change those things, it will change other variables, right? If I increase one of these, I may decrease another. So in Boyle's law, we are looking at the relationship between just pressure and volume. So give yourself a note here that says that temperature and amount, little n, is constant. So we're not going to change temperature and we're not going to change amount of gas. We're going to assume that those stay the same. So the pressure of a gas is in part dependent on its volume. These are what we call inversely related. So as one goes up, the other goes down. So the pressure of a gas sample increases for a decrease in volume and decreases for an increase in volume. So if I decrease the volume, if I take the same amount of gas and I squeeze it into a small volume, the pressure is going to increase because you have more collisions over a smaller area. Vice versa, if I take a canister of really compressed gas and I increase its volume by opening that canister into a big room, what happens to the volume? It decreases. A bike pump. Yeah, what's up?
On the PV&T, my internet cut out. Sorry. That was pressure, volume, temperature, and what was the N?
N is amount, specifically the amount in moles. Okay, so you may be given something in grams. You're going to want to convert it to moles. The your cat, Terry, your cat is cracking me up. The amount in moles will be how it relates to volume and temperature and things like that.
Okay, thank you.
So if we think about a bike pump, right? If the plunger on the bike pump is at the highest point, we have a big volume and a relatively low pressure, right? It's easy to push the plunger down in the beginning. What happens when you get towards the bottom of the shaft though, right? You have taken this air and you've compressed it into a smaller volume. It's harder to push down. You have more resistance or more pressure. That forces the air through this to fill up your tire. So Boyle's law is, again, I said inversely proportional. This thing here is not the actual equation. This is just saying that volume is inversely related to pressure. As pressure increases, so if pressure goes up, the volume will go down because the pressure is below the fraction bar. But what we want is the equation. And I don't know why they don't give us the equation, but they don't give us the equation. Okay, so let's write some of this out here. So we got Boyle's law. We said that temperature and amount are constant. We also said, so it's going to relate pressure and volume, and pressure will be inversely related to volume, or volume is inversely related to pressure. This is the equation. P1 V1 equals P2 V2, where the ones are your initial and your twos are your final. So this equation you'll be using it when there's some sort of change in the variables, right? I have an initial pressure and then the pressure changes to something in the end. The volume will shift according to that change in pressure. There are how many variables in this equation? 4. So when you are looking at a problem, you will be given 3 of the 4 variables, okay? And you'll solve for the 4th. I think these are not hard equations. The biggest thing that I see for people is that they won't have the units the same on both sides. So make sure you have the units the same. And they'll put some of their initial information in with the final stuff. You want to keep those separate. Okay, so you want to identify what is my starting parameter and what are my ending parameters, keeping those separate from each other. So let's look at a problem. I got this guy here. A cylinder equipped with a movable piston has an applied pressure of 4 atms and a volume of 6 liters. So there's a pressure and there's a volume. What is the volume of the cylinder if the applied pressure is decreased to 1 atm? So how do we know that we need to be applying Boyle's law outside of the fact that it tells us at the very top it's Boyle's law? Well, we're seeing a change in our parameters, right? So there's an initial set and there's a final set. And what are the only things they're talking about? They're just talking about pressure and volume. Do you see anything about temperature? Nope. Do we see anything about gas amount? Nope. So Boyle's law will be the one that we use. So P1 V1 equals P2 V2. We want to go ahead and list out all of our parameters. I think they have it laid out step by step, so we'll go through that. I have to deal with my hand writing. Okay, so P1 is our initial pressure. Our initial pressure is 4 atms. Our initial volume is 6 liters. Again, you really want to make sure that you're putting the right value with the right number, right? Because these two things need to be paired with each other in the equation. The final pressure is 1 atm. So we are going to solve for the final volume, V2. We need to isolate for V2. Some people like to just plug it into the equation. This is the equation here. They just like to plug it in and then get V2 by itself. I like to isolate my equations first and then plug the information in later. So P1 V1 equals P2 V2. What do I want to do? I want to get V2 by itself, right? So here's our V2. I want to get it alone. So what's the only thing I need to do? I need to move this P2 over to the other side. Well, what is P2 doing on this side? It's acting as a multiplier. So I need to divide this side by P2 and divide this side by P2 as well. Whatever you do on one side, you have to do on the other. What happens to P2s over here? They cancel, and we're left with just that unit of V2. So V2 equals P1 times V1 divided by P2. There's gonna be a lot of variable isolation in this section. So if that's a rusty point for you, you will want to review it. So there is the equation, the way that I find it a little bit more useful. Again, you could have plugged all the data in here and done this after the fact. Add the units when you're going through this, okay? Don't just write 6,4 divided by 1. Write in liter ATM, because that's a good way to remind you, like, what if this unit is an ATM and this is in millimeters of mercury? Well, right away you can see, oh crap, I forgot to convert one of them, okay? It also lets you know if you've like plugged it into the equation correctly, because the units should fall out in such a way that the remaining unit matches what you're trying to find. And what were we trying to find here? A volume value. Is liter an appropriate unit for a volume? It is. So we take the 6 times 4 and divide it by 1, or 24 liters. The last thing I like to do is just, conceptually, does it make sense? So going back to the original problem, I was at 4 ATMs and that took up a volume of 6 liters. I decreased to 1 ATM. So what did I do with my pressure? My pressure decreased. So what should happen if pressure decreases? Volume needs to increase, because those are inversely related to each other. Does my volume increase? Oh yeah, and it increases by a factor of 4, right? My pressure decreased by a factor of 4, 4 to 1. My pressure increased by a factor of 4, 6 to 24. So a nice little clean, nifty equation. I'm going to keep going with all the equations, and then we'll do a bunch of practice after we've sort of gone over all of them. So this is the first one, Boyle's law. All right, snorkels, extra long straws, great. The next law that we're looking at is Charles' law. So why does hot air rise? Why do air, how do air balloons work? All these things. It's going to relate volume and temperature. Okay. Because we're looking at just volume and temperature, make a note that for Charles' law, pressure and amount stay constant. So we're not going to play around with pressure, and we're not going to change the amount of the gas. We're just looking at volume and temperature. So volume and temperature are directly related to each other. Let's see, it says here, so volume and temperature are directly related. When I increase my temperature, my volume is going to increase as well. If I decrease my temperature, my volume will decrease. Looking over here at this hot air balloon, this is a perfect example of Charles' law. What is happening here? Well, I have air inside the balloon. The air inside the balloon is being heated by that big like flamethrower that they have attached at the bottom. It heats the air up. As the air heats up, as we increase the temperature, we increase the volume. But have I changed the amount of the gas? Not really. I've just increased its volume. So that decreases the density, right? Bigger volume, same amount of gas, lower density. This is a lower density air than the air around it, which allows it to float. So we're keeping the pressure and the amount of gas the same. And here is a picture of what happens, or a graph of what happens. So as I increase the temperature, I increase the volume. Straight line here. Now, as the gas gets colder and colder and colder, it's going to take up less volume, right? At some point, we are going to get so cold that our gas takes up ideally 0 space. Can we get colder than that? No. This is one reason why, if you've ever wondered what absolute zero is, like why is it negative 273 Celsius? It's because if we went any colder than that, gases would end up taking up a negative amount of space, right? They would take up less than 0 space. Not possible, okay? At that point, all atoms would cease to move and gases would take up no space. We can't do that. So that is sort of our cutoff point of the coldest point we can get to. So absolute 0, 0 degrees Kelvin, colder temperatures don't exist. Remember, converting between Kelvin and Celsius, sorry about that, is just a quick shift of 273, right? If we want to get into Kelvin, we just add 273. For this equation, okay, the previous equation for Boyle's law, as long as the units are the same on both sides, like you're using ATM and ATM, or you're using milliliter and milliliter, you're fine. Okay, they just need to be the same on both sides. This one though has a constriction on on temperature. Temperature has to be in Kelvin. If you want to use this equation, do not put Celsius in that. Do not put Fahrenheit in it. It will not work. Okay. If they give you information in Celsius and they want it to come out in Celsius, you first have to take Celsius to Kelvin. Then you get to plug it into the equation, get a Kelvin, and then convert back to Celsius. Let's see, it gives us a couple other, so it talks about them being directly related. So as one goes up, the other one goes up. And it's, you know, as you triple one, you triple the other. So if I increase my temperature by a factor of 3, my volume will increase by a factor of 3 as well. It's directly proportional. Here's a visual of Charles' law. If I took a balloon, tied it off so it had a consistent amount of air, and I put that into an ice bath, the balloon would appear to shrivel up. Why is it shriveling up? Because the gas is contracting. It's taking up a smaller volume. If I took that same balloon and I put it in boiling water, hopefully it wouldn't pop. What we would expect the balloon to do is expand because the gas is taking up a broader volume. Here's the equation for Charles' law. So V1 divided by T1 equals V2 divided by T2. We don't talk about pressure and we don't talk about amount here. So we assume those are constant. I know it looks like they're inversely related, but these are directly related. As one goes up, the other one will go up. So let's look at this equation here. I want you to do this one. Remember that you cannot get Celsius in that equation. You have to convert to Kelvin. So this one says, hey, a sample of a gas has a volume of 2.80 liters at an unknown temperature. So you don't know the initial temperature. When the sample is submerged in ice water, and we know ice water is 0 degrees Celsius, its volume will decrease to 2.57 liters. What was the initial temperature, both in kelvins and degrees Celsius? Okay, so use Charles' law here. There's 4 variables. You're given 3 of them. Make sure you're in Kelvin. I'll give you all 2-3 minutes for that guy. Okay, so when looking at this one, you know, again, Charles' law isn't going to be written on the top of the problems that you're working on. So you want to say, oh, we're talking about temperature, we're talking about volume, and we're seeing a change. So I'm going to have initial and final parameters. So we're going to use T1 over V1 equals T2 over V2. You've got all your equations here. Here's our equation. So we want to isolate for T1, right? This guy over here. This is something that I see a lot students having struggle isolating variables, especially if it's underneath the fraction bar. So I'm just going to go over that real quick. On two different ways you can sort of isolate those. Come on now. Okay, so we've got V1 over T1 equals V2 over T2. We need to get T1 by itself. So in order to do that, there's a couple different ways you can go about it. One thing is you can move V1 to the other side. Okay, so what am I going to do? I'm going to divide this by V1, and then I'm going to divide this by V1. Now, the important thing here is that look at where T1 is. It's still below the fraction bar, right? A lot of times people will do this and they'll be like, yay, I'm done. Okay, T1 equals V2 over T2 times V1. That is not the case. Actually, what we have going on here is 1 over the T1 equals this setup here, V2 over T2 times V1. Okay. So I need to flip these. And if I flip these or take the inverse of these, I need to flip the position of these. So T1 will actually equal these guys being on top, T2 V1 over V2. Okay, flip flop. So what I don't want you to do is go from this thing, say, oh, I'm getting rid of the V1, I'm moving it to the other side, and then you're like, I'm done, yay, T1 equals all that stuff. No, it's still sitting under the fraction bar. So you do need to take that into account. Another way you can isolate that guy, what did we say? T1, nope. V1 over T1 equals V2 over T2. So what we can do is, when I'm looking at this, I see, oh, T1, which is what I want, it's under the fraction bar. I just don't like it being under the fraction bar. I want it to be the top. So I'm actually going to move this to the other side. So I'm going to multiply this side by T1, and I'm going to multiply this side by T1. T1 goes away, and now there's my T1, and it's above the fraction bar. I like that. Now I'm going to get rid of this stuff. Okay, how do I get rid of this stuff? I do the opposite. So if V2 is on top here, we need to divide it on the bottom. If T2 is on bottom, we need to multiply it, right? That will allow these to cancel and these to cancel. Whatever I do on this side, I have to do on the other side. So I'm going to add T2 on top, V2 on the bottom, V1. So we end up with T2 times V1 divided by V2 equals my T1. This is the same thing as this up here. Okay. Two different ways of going about it. If you're like, isolating variables are horrible, spend a little bit of time trying to get that, because this whole chapter is just variables and equations like this. Back to the slide here. So there's our Charles. Oh, we didn't even. All right, so we've got those. We know the equation we need to use. We need to isolate for our equation. So this is the equation that we came up with. T1, the initial temperature is equal to V1 divided by V2 times T2. We need to get T2 into Kelvin. Kelvin is the only thing that can touch this equation. So put your, and again, it's really important to have those little numbers in the right spots, because we need to be plugging the right numbers in. So your initial volume was 2.8 liters. It decreased, the volume decreased to 2.57 liters. And then we're gonna multiply it by 273 Kelvin. So we end up getting a final temperature of 297 Kelvin. Remember, it plugs it out. You gotta put it in Kelvin, it's gonna plug it out in Kelvin. So I think the problem also asked us to get it in Celsius. So real quick conversion, 297 minus the 273 gives us 24 degrees Celsius. So it's just plugging and chugging. It's like, depending on where you were in school with math and stuff. I mean, we're talking like 8th grade math here. Okay, it's just equations, plug and chug. Any questions on that? We will do more practice definitely a little bit later. I just want to get through all the equations first. But any questions on like the concept of how that works? Really just organizing and plugging. You're feeling like this kind of feels a little easier than what we did before. I think it's a lot easier. As long as you have the equations, it's just a plug and chug. We can do something funky. We can do what's known as the combined gas law. So we can actually take those two previous equations and smoosh them together. So in the combined gas law, we're going to look at the relationship between not just pressure and volume or volume and temperature, but we're going to look at pressure, volume, and temperature. What's the only thing left out? What's constant here? The amount of gas, our N value. So we're not changing how much gas we have, but we're playing around with its pressure, its volume, and its temperature. Here it is. It's the two of those previous equations combined. So P1 times V1 divided by T1. You can see this here is the Boyle's law portion of it. This here is the Charles law portion of it. So we can put them all together. P1 V1 over T1 equals P2 V2 over T2. How many variables do we have in this one? 6. So how many variables will you have to organize and be given? 5 to solve for the 6. Again, pressure can be in whatever unit as long as it's the same on both sides. Volume can be in whatever unit as long as it's the same on both sides. Temperature has to be in Kelvin. So here is, look at this beaut. A sample of gas has an initial volume of 158 milliliters. So write that out. V1 is 158 milliliters. It has an initial pressure of 735 mmHgs, an initial and an initial temperature of 34 degrees Celsius. Those are all our 1 values. If the gas is compressed to a new volume of 108 milliliters, so second volume, V2, 108 milliliters, and is also simultaneously heated to a temperature of 85 degrees Celsius, so T2 is 85, what is the final pressure, specifically in millimeters of mercury? Which is great that it wants it in millimeters of mercury because what's our given pressure in? Millimeters of mercury, so it should just pop right out. So I'm going to have you guys plug that into that previous equation. Let me write it out. If you didn't write it down, P1 V1 over T1 equals P2 V2 over T2. So organize your information, isolate for the variable that you're trying to solve, plug it all in, make sure you're plugging it in with the units, and solve. And we'll come back together in about 2 minutes. So let me clear this out. So again, how would you know it's a combined gas law? You're seeing initial and final parameters, and it's talking about 5 different things and asking you for a 6th. So here's all our stuff. We want to get P2 by itself, this guy over here. So I need to put, if V2 is on the top here, I need to stick it on the bottom here. If T2 is on the bottom here, I need to stick it on the top over here. So your final isolated equation should look like this. Your final pressure should equal the initial pressure on the top, the initial volume on the top, and the final temperature on the top, divided by the initial temperature and the final volume. Okay? Get those temperatures right away. Anytime you're in this chapter, get the temperatures into Kelvin if you're going to use them in an equation. Okay, so we've got a 307 and a 358. Plug them all in, and this again is a reason to put the units in, because you can see, oh, there goes the milliliter and there goes the milliliter, right? There goes the Kelvin and there goes the Kelvin. You don't have to convert milliliters to liters in these before and after ones. Kelvins go, milliliters go, and we'll be left with just millimeters of mercury. Looks like when we plug all this in, we get 1.25 times 10 to the 3rd millimeters of mercury. Remember, 10 to the 3rd, just move the decimal over 1, 2, 3, or you guys should have gotten 1,250 millimeters of mercury. So it's a plug and chug chapter. One more equation I want to look over before we go today is Avogadro's law. Avogadro's law is going to look at the relationship between volume and moles. So this is the first time you guys are seeing like the amount actually brought in. If we're looking at volume and moles, what's staying constant here? We're not changing pressure and we're not changing temperature. Okay, so don't worry about pressure or temperature with these. Here's a graph that shows you as the number of moles increases, what happens to the volume? It increases. So these are directly related to each other. As volume goes up, the amount goes up. As the amount goes up, volume goes up. There's a real easy example of where to see this. Think about blowing up a balloon, okay? What do you do to the balloon? You are blowing in moles of gas. So what happens to the volume? It gets bigger. They're directly related. And then we've got the equation, which it doesn't give you, but it looks very similar to Charles' law, except with different variables. So let's see here. So Avo's law is V1 over N1 equals V2 over N2. So your initial volume divided by your initial amount, and this has to be in moles, is equal to your final volume divided by your final moles. Again, volume can be in whatever unit you want as long as they're the same. Moles, though, needs to be in moles. Go over here and they give us an example. It says, hey, a 4.8 liter sample of helium gas contains 0.22 moles of helium. It's important here. The problem is saying, hey, how many additional moles of helium gas should you add? When it says how many additional moles, it's not necessarily asking you for the final number of moles. It's asking you for the difference between the final and the initial, right? So you have to do an extra step there. So we still want to solve for the final amount. We're still going to do that. We've got our initial volume, we've got our final volume, we've got our initial amount. Let's solve for the final amount. So we do that using this equation here. We want to solve for N2. N2 is on the bottom right-hand corner. So to isolate, we need to move it over to the other side and flip-flop, or N2 will equal V2 divided by V1 times N1. We plug that in, and what we will end up getting is 0.29 moles. Okay, so we initially had 0.22 moles, Now we have 0.29 moles. So the amount of gas increased, which makes sense because our volume increased. Now the question, refine that a little bit. It says, how much gas did you have to add? Not how much gas did you end with? We ended with 0.29, but how much did you have to add? Well, if we started at 0.22 and we're ending at 0.29, let's find the difference between those two. Okay, so we take the final minus the initial, and we end up that we added 0.07 moles. So with the Avogadro's problem, just make sure you read, is it asking you for the final amount of gas, or is it asking you for how much gas you had to add? Okay, if it's asking you for how much you had to add, you want to find that difference. And those are all the before and after equations. Okay, so we've got Boyle's, Charles, combined, Avogadro's. There is another one called Guy-de-Sax's law, which relates pressure and temperature, but we're not going to look at that one. But all the equations that we've talked about thus far have been a change in, right? You have a given amount of a starting and you change it to some sort of ending amount. We are going to next time look at the ideal gas law, which is sort of a scenario where we're frozen in time. All right, we're not changing anything. We're given a certain pressure, a certain volume, a certain amount, and we want to find temperature. We're not changing it. We just want to know at that given second what's going on. So we'll come back to PivNert next time. We will do some more practice with the other ones too, once we've gotten through PivNert. So we'll stop there for today. If you have any questions, stay around. If they're open for people hearing, you can just shout them out now. If they are something personal, just wait around and we can talk about it. Otherwise, enjoy the rest of your day, and I will see you all on Wednesday. Don't forget to take your test if you haven't taken it yet by midnight tonight. Okay, everyone.